Before we start, let me make two quick announcements. We have a discussion session this afternoon, and I asked Scott and Manoj if they would lead the discussion. So we'll do it like we did last week, and maybe at the end of Kyle's lecture, I'll think of some crazy way to split the classroom, and then half of you go downstairs, half up here, and swap the lectures back and forth like we did then. Okay. So that's announcement number one. Announcement number two. It's really important for those of you that have cards. Next Thursday, I believe, the Dalai Lama is going to be in Boulder. Okay, and Boulder was full of Buddhists before the Dalai Lama showed up, and the Dalai Lama is doing a service over at the Tourist Event Center. So I am not making this up. Okay, I don't know if that's okay. I'm an old Presbyterian. I don't know what to call it. Anyhow, so if you have a car. And you are on campus, and you are registered with the university, they will, for a parking permit, they will have sent you an email message because there's going to be stuff closed all over the place. This is going to be like, the Dalai Lama is going to be like when Obama was here. Okay, things are going to be shut down all over the place. So just be aware. Okay, if you got a car, if they tell you to move it because otherwise, the car will be levitating. Okay, so.
Okay. Yeah. Good morning. I enjoyed talking to many of you, or some of you, last night. It reminded me again of why I feel so fortunate to be a physicist, meeting such interesting people. It was really fascinating talking to many of you from different countries. I want to continue the discussion about the power spectrum. So let's close the loop a little bit and first talk about the shape of the power spectrum. By the way, keep in mind what Manoj set up for us with lensing, because tomorrow we'll just talk solely about lensing. Gravitational lensing and galaxy surveys and CMB lensing that Nilima also kind of give you a hint of. So tomorrow's lensing, but today let's finish up the what we started on the power spectrum of matter. So we didn't quite close the loop. We learned that perturbations grow as the scale factor when in the epoch in which the universe is matter dominated, and we know that's roughly from when the scale factor is greater than 3 times 10 to the minus 4 until recently. What I didn't say, but what is true, is that perturbations are roughly constant. In the radiation-dominated era. And that kind of makes sense because it's hard for stuff to grow because radiation just flows out of a perturbation. So without any equations, I'll ask you to accept that. The other thing I didn't say is we did talk about the horizon, modes entering the horizon. So when a mode enters the horizon, roughly speaking, this quantity delta that we talked about, which is the overdensity of matter, is of order the gravitational potential, roughly. So that's another thing I didn't say. And then the final thing, which I will try to justify in about a half hour, is that the perturbations, the initial perturbations, let's call them primordial, the primordial spectrum, the thing that happens before evolution begins, right? Because you have to start with some spectrum initially, and that evolves. So the primordial spectrum is scale invariant. So that's a technical term, but you now know what it means because we did this decomposition in terms of Fourier modes, and we saw that, say, the variance of a given field goes as the integral dk over k times k cubed p of k, right? So scale invariant means that in every logarithmic integral in k, dk over k, k cubed on the power spectrum is constant. That's what scale invariant means. That, the k cubed pk quantifies it's a dimensionless quantity, right? And that dimensionless quantity could depend on scale. If it's scale invariant, it means it's the same in all scales. Does that make sense? So with one little caveat, and that is, maybe not so much a caveat, but remember, since this is true, it's simplest to, I can just do it like that. Okay, good. So let's just say that k cubed p of k is constant, roughly constant. And this is something that's interesting because it has a scale invariant spectrum is called a Harrison-Peebles-Zeldovich spectrum. It's named after three people who lived and postulated the idea because it's a natural idea. And the idea existed before Alan Guth came with the idea of inflation, which enables you to generate this dynamically with small deviations from it. So the scale invariant spectrum is interesting. Historically, you would have thought it's kind of the first thing any smart person would think of. But we now have a mechanism for generating it. And the interesting thing is, in most inflationary models, the spectrum is not exactly scale invariant. And in fact, it's been measured recently to be not scale invariant at the 5 sigma level. So that gives us confidence in this whole idea of inflation, that we have a dynamical mechanism. It roughly gives what you would have expected, but it makes predictions that it should be slightly different, and we've measured it to be slightly different. So that's quite a nice thing. Okay, take these three things, and let's talk about what the power spectrum looks like. Yeah? Good. You're asking an observational question? Okay, so the cosmology is sensitive to only a small range of scales, from roughly a gigaparsec to 100 to 10 megaparsecs. So it's really only 3 or possibly 4 orders of magnitude, depending on how ambitious you are. However, there are ways of actually extrapolating very, very far forward. For example, the primordial black holes. That's one way people think of doing it. And another way people think of doing it is, you might have heard that recently some obscure group detected gravitational waves, and so there are plans for the future distance to measure gravitational waves at those or slightly lower frequencies that would be produced during that are cosmological in nature. And that would increase the lever arm by a factor by like 10 orders of magnitude or something like that. But right now we're confined to roughly 3 orders of magnitude. Other questions? Okay, so let's take this and let's try to write the evolution of a bunch of Fourier modes. So as a function of time, so again, using scale factor as time, this is 1. This is 10 to the minus 3. And the magic number, yeah, is that a question? No. Okay, the magic number, sorry. The magic number is the epoch of equality when radiation and matter are equal, and that is equal to 2.95 times 10 to the minus 4 and actually there's another decimal point that I just forget, so it's measured extremely well. So we know that. Okay, so now let's talk about modes. So what we'd like to plot then is what we'd like to plot. Remember, the power spectrum is the square of the amplitude of a Fourier mode, right? So the thing that we'd like, if we're interested in the evolution of a given Fourier mode, what we're interested in plotting, if we want them all to start with the same amplitude, let's plot k to the 3/2 times delta twiddle of k. Right? Because that's something that they all start at the same value. Right? So that makes sense. That makes sense to me. And let's first look at a very large scale mode that has a wave number k equal to h0, the current size of the horizon. So that mode, any guesses as to how that would evolve with time? Active learning. K equals h0, which means it's a very, very large scale mode. It's just the size of the horizon today. So to give you a hint, that means it's been outside the horizon until today. Great. Okay, good. So this is k, let's call it k1 equal to h0. how about K2 equal to 10 H naught? It enters the horizon earlier. Good. When does it enter the horizon? So it enters the horizon when K2 is equal to, let's call it AH2, right? And that, remember, H, so this is equal to H naught. Let's just pretend that all there is matter. So then this is H naught, and H, remember, scales as the square root of the energy density. If the energy density of matter scales as a to the minus 3, H scales as a to the minus 3/2. Do you agree? So this is a times a to the minus 3/2. It's a to the minus 1/2. So this second mode enters the horizon. If K2 over H naught is equal to 10, it enters the horizon when A2 is equal to what? Is equal to 1 over 100. Do you agree? Square root of 10, right? So that means it enters right here. So that mode, until it enters the horizon, it's constant. It enters the horizon when A is 10 to the minus 2. But let's just put in numbers here. Let's say the initial amplitude is 10 to the minus 4. So and it grows. How does it grow? Linearly in A. So it grows by a factor of 100 from the time it enters the horizon. So that means this quantity over here is 10 to the minus 2. Right? So and this is for a mode that has K2 equal to 10 H naught. So what does that mean? What that means is the amplitude of K1 over the amplitude of K2 today, which is when we measure it, that amplitude is equal to, well, they start off with an amplitude that scales as a constant over K to the 3/2, right? So initially they start off with a ratio of K2 over K1 to the 3/2. Right? But then this one has grown by a factor of 100. Right? It's grown by a factor of K2 over K1 squared. So what that means is the ratio of these two goes as K1 over K2 to the 1/2 power. Right? And the square of it is the power spectrum. So this implies that modes that enter the horizon after equality, so these are low K modes, ones that enter the horizon after equality, they have a power spectrum that is proportional to K. Does that make sense? That follows from the scale invariant assumption. Other questions? Okay, let's do a slightly, actually this turns out to be a little bit easier. Let's take K3 equal to, let's call it 1,000, or let's call it 100, let's call it 1,000 H naught. And K4, or let's call it 100, fine. 100 H naught, and now let's call it 1,000. 1,000 H naught, and K4 equals 10,000 H naught. And this is really, if we talk about the modes that we can measure, this really spans the full extent from H naught to 10 to the 4 H naught. That's roughly the total number of modes we can. So what about K3? Active learning. Great. So there's an assumption there. Why till equality? Great. Okay, good. So it starts off here. It's outside the horizon. It enters the horizon, but then nothing happens, right? So it's here, and then what happens? And then it grows as a squared, right? So that grows as a squared. So the amplitude is this K3 equals to 10 to the 3 H naught. That one has an amplitude which has grown by a factor of this factor squared, this factor AE, 1 over AE, right? So a factor of roughly 10 to the 4. So, okay, what about K4? Same thing. Very good. right? Because nothing happens until then. So what does that mean? That means that the amplitude of K3 over K4 is equal to, the evolution is the exact same thing. So the only thing that changes is this initial stuff here. So it just goes as K4 over K3 to the 3/2 power. So this implies that high K modes have a power spectrum K that scales as K to the -3. And what that means is the power spectrum is going to have a pretty simple shape. For low K, it just goes as K. And for high K, it goes as K to the -3. And the place where it turns over is going to be precisely the value of K which enters the horizon at equality. Right? So that turnover scale is called K-eq. And K-eq is just determined by the notion that it's equal to the epoch of equality times the Hubble rate at equality. So we can actually calculate in numbers what that is. Remember, AEQ is the epoch at which matter is equal to radiation. So that's just the ratio of the matter density to the radiation density, because radiation goes as omega radiation over a to the 4th. Matter goes as omega matter over a cubed. So the time when they're equal is AEQ is omega radiation over omega matter, right? So this is equal to this thing over here. Let's leave it at AEQ for a second. But remember, that's equal to omega radiation over omega matter. And that is a number, which is 2.95 to 10 - 4. AEQ is the square root of omega matter times AEQ to the -3 plus omega radiation AEQ to the -4. And then there's an H0 out in front. Right? But these two things are exactly the same. That's how we defined them, right? So it's just equal to the square root of, let's see, there's a 2, because there's 2 of these things. There's an H0 squared. Let's just focus on that one. There's an omega matter. AEQ to the -3, and you put that inside, it becomes AEQ squared, so it just goes over AEQ. So that's the answer. This is measured extraordinarily accurately. I think Nalima gave it to you. This is about 0.11 or something like that, maybe 0.13. And this is known extremely accurately. So you just plug in numbers. This is 0.008 inverse megaparsec. Okay, so that's the shape of the power spectrum. Very simple and has that form. Questions? Okay, second point. So Manoj is sitting here. Let me refer you to a beautiful article that Manoj wrote in 2003 about the impact of massive neutrinos on the power spectrum. So if neutrinos have mass, then they contribute a lot to the energy density. And what they end up doing is, what is the difference between neutrinos and WIMPs? WIMPs are very heavy, and they move very, very slowly. The ratio of their thermal velocities, T, to their rest energy m is 10 to the -12, 10 to the -20, whatever. It's incredibly small. Whereas for neutrinos with masses on the order of electron volts, they move pretty rapidly. So even today, they're moving with velocities of order 10 to the -3, not too slow. So what that means is if you have a perturbation with lots of cold dark matter in it, there's some scale, let's call it the free streaming scale, that neutrinos just randomly, because of their thermal velocities, are able to escape out of. So they won't be trapped in that scale. That means perturbations are suppressed on scales smaller than that free streaming scale. So the power spectrum is suppressed on scales smaller than k greater than 1 over lambda free stream. So it's the thing that Manoj did in the article. I don't even know if it was ever published. Was it? You know what I'm talking about? Okay, was it published? Yeah. Anyway, but you can find it somewhere, right? So I think I'm going to reproduce 2 graphs from there. Tell me if I'm wrong. Anyway, this is where I learned all this stuff from his article. So what is the free streaming scale? How fast can neutrinos travel, say, in a given time? Okay, well, okay. They can, okay, good. So it depends on their velocity. Right? That's true. So the free streaming scale is proportional to the velocity. And also, I have to tell you how much time we're talking about. So it's proportional to the time. The longer the time, the longer they can travel. That's the physical scale they can travel. But remember, in cosmology, in all this power spectrum stuff, we're talking about co-moving scales. So you have to divide by the scale factor. 2 more things to know. The time, t, is always roughly equal to 1 over h. So this is equal to 1 over ah. The velocity, this may surprise you, is, any guesses for what the thermal velocity is? Say it again. They're non-relativistic. Let's say they're non-relativistic at late times. Sorry? Yeah, let's say when the temperature is beneath their mass. Let's say they have a mass of an eV. The velocity has got to be dimensionless. Good. Okay, I'll take that. T over m. T nu over m nu. Okay, good. So that's the right answer. So what does this mean? The temperature scales as 1 over a. That goes 1 over a squared. H during this late time matter epoch scales as a to the minus 3/2. We learned that before. So this whole free streaming scale is time dependent. It depends on a. It scales as a to the minus 1/2. And if you plug in numbers, it's roughly equal to a megaparsec. And you know all the numbers to plug in. If the neutrino mass is 1 electron volt, because you know the neutrino temperature, you know what the it's the photon temperature times 4/11 to the 1/3, and then there's this thing, you know all that stuff, and then the only thing left is to say that it scales as a to the minus 1/2. So again, we can plot this as a function of time. So this is the first thing I think is in Manoj's paper. So today, let's do it for 1 eV neutrino mass. Today, the free streaming scale, let's do it in megaparsecs, is 1 megaparsec. That's over here. But at early times, when structure began to form at a eq, say 10 to the minus, when a is 10 to the minus 3 or so, sorry, my son is stuck in Berlin trying to get to Edinburgh. I've been on the phone for an hour with him and whatever, it hasn't worked out. Okay, so anyway, I've been on texting him for literally 45 minutes, going back and forth to travel agent, and right before he just sent me a message saying, "Forget about it, I'll take care of it." So okay, so that teaches you something about parenting. All right, so anyway, where was I? At 10 to the minus 3, a is 10 to the minus 3, so this is roughly going to be 30. So it'll be 30 times bigger. So this is going to be 30, and so that's what this looks like. And so this is the first thing. So what does that mean? That means that on scales smaller than this, growth is suppressed. There's less. These scales don't grow. I spelled suppressed. So what that means is that this scale, a scale of 30 megaparsecs, will only be suppressed for a small amount of time, right? And a scale of 50 megaparsecs won't be suppressed at all, right? So little suppression. whereas this scale of 1 megaparsec or anything smaller than that is going to be completely suppressed. So these scales and below are fully suppressed. So what that means is when we come to plot the power spectrum, we know exactly what it's going to look like. The ratio of the power spectrum with the mass of neutrino divided by the power spectrum with m nu equal to 0, the ratio of that power spectrum as a function of k, and then k is an inverse megaparsec. This is 1. This is 10 to the minus 2. 10 to the minus 1. So, and this is 1. So on large scales, it's 1. And on small scales, it's going to be suppressed. And then once you get past 1 megaparsec, the suppression is just constant because all those scales have been suppressed by the same amount, right? Some fraction of the matter, whatever the fraction neutrinos are, they will not have been able to participate in this cosmic growth. They've broken the tie, remember, between expansion and between expansion and gravitational accretion, and therefore the total matter, the total growth of matter will have been suppressed by this amount. How much? Turns out this suppression is of order 10 times f nu, where f nu is the ratio of neutrinos to the fraction of neutrinos to matter, which depends on the neutrino mass in the way that we calculated. So it's a fairly large suppression, and that traces itself back to this delicate balance. Once you break the balance by taking away even a small fraction, even if f nu is like 1%, right? You're breaking a delicate balance, and therefore you're suppressing growth in the rest of the structure. Yeah. Okay, it's a good question. It turns out this number is probably 8 in linear theory. It's 10 in nonlinear theory, so it actually exacerbates it. However, recently there's been a lot of work spurred by Marilena Loverde and now Wayne Hu and company suggesting that some of this suppression might be counterbalanced by what's called biasing. So some beautiful papers just last month by Wayne that you might be interested in. So this is still not. This is the power spectrum of matter. However, a lot of the strongest limits come from observations of galaxy surveys that tend to assume that the galaxies trace the matter pretty simply, and that assumption is now being called into play. So a lot of the limits on neutrino masses in my mind now are a little bit suspect. Other questions? Yeah. This is the power spectrum if neutrinos have a mass of 1 electron volt, divided by the power spectrum if neutrinos are massless. If neutrinos are massless, they don't contribute very much to the energy density, just as much as photons, 10 to the minus 5. So it's basically nothing that nothing happens here. I wrote that. I think it's omega nu h squared is equal to the sum of the neutrino masses divided by 94 electron volts. Other questions?
So basically, the mechanism for suppressing this structure is similar to basically the normalized.
No, silk dancing is different, right? So the damping. It's a good question. It's a very good question. We talked about this after class last time. After the lecture last time. The photons can free stream, can random walk out of a given region called the free streaming scale, and that leads to the damping tail in the CMB. That's what you're referring to, right? That damping tail in the CMB means that it's hard to keep structure formed on those small scales because the photons are scattering off electrons, and in a given cosmic time they random walk out. Neutrinos are not random walking because they're not hitting anything, so they're just free streaming. So in that sense, it's different. It's same kind of impact. But it's different physics. Yeah.
So in other words, the amount of structure that is formed by subtract from the net.
It's not an algebraic thing. You have to solve the growth equation, with saying only a fraction of matter participate in growth on these scales. And because of that delicate balance, that tends to really mess up, that tends to suppress the growth quite a bit. Okay, I want to talk very briefly about inflation. Because I said that the initial perturbations are scale invariant, and that our best model for that is inflation. So let's just very briefly talk about that, invoking a diagram that we drew last time. So we had this diagram that showed, I guess, distances, co-moving distances. And then there was the co-moving distance corresponding to a given cosmological wave number is constant. That's what co-moving means. And we compared that with the inverse Hubble, with the Hubble distance, the co-moving Hubble distance, remember? And that was something that was decreasing with time. Sorry, that was increasing with time. Remember we had this yesterday, right? So this is a kind of a fancy way of writing down what's called the horizon problem, which says, let's say that this is where A-eq is, or this is where recombination is. Well, you have these scales on the sky that are separated by huge distances, right? So maybe in real space it's a little bit easier to think about it. Remember those CMB maps? There's a spot on the sky here and a spot on the sky here. The Hubble radius at which is the distance of causality, right? So this is 1 over AH. So that co-moving Hubble distance is the distance within which things are causal. So that's corresponding to each of these circles, right? So it's way smaller in this case than cosmological distances that are actually measured on the sky. So we measure correlations in the CMB between things at very large angles, very large distances, right? So that means that, but this is causal within here, and this is causal in here, but they had no chance to talk to one another. So what set up those correlations? That's the question. It seems impossible to do because if you think where they set up back early in time, things got worse. The causality radius was getting smaller, so only scales inside here could have got it. So these cosmic scales could never have been within the horizon. They could never have been no causality could ever have been imposed on them. So that's the horizon problem. And the solution is that there's new physics. We derive this assuming just matter and radiation. So there's some epoch at which there was new physics, and that physics led to a decrease in the co-moving Hubble radius. And this epoch is called inflation. So a decrease in the co-moving Hubble radius means the derivative with respect to time of 1 over AH, which is 1 over h is the co-moving Hubble radius. That's got to be decreasing. That's got to be less than 0. But remember, h is a dot over a. So this says the derivative with respect to time of 1 over a dot is less than 0. So when you take that derivative, what this implies is that a double dot is greater than 0. So what that means is inflation, you had to have an epoch in which the universe was accelerating, just like our current epoch of acceleration. We actually know quite a bit about that. We learned that in order for that to happen, we require W to be less than minus a third. That is, the pressure to be less than minus rho over 3. Right? So that's the requirement for inflation to have happened. And one way to implement that is to introduce, as Neil suggested yesterday, a scalar field. So with a scalar field, so inflation driven by a scalar field. So the pressure is equal to 1/2 phi dot squared minus the potential, and the energy density is 1/2 phi dot squared plus the potential. We require the pressure to be negative, which means this term has got to be bigger than this term, right? And so what roughly this implies is that the field has to be slowly rolling, probably, right? Because you want this term to be dominating over this term. I'm sorry? Yeah, exactly. Okay, so that's the basic idea. And then the last thing is that in order to, during this epoch, this is the epoch in which perturbations were generated, right? Because that's exactly what we see in the sky today. So the picture is quite stunning. This is the picture then you should have in your mind. Really, everybody should have in their mind. This is our current story of our creation. So we really should have this picture in mind. So this is a given, let's say, the gravitational potential, which is what we've been focused on. So during inflation, all the fields, this inflation field and all the fields it couples to, for example, the metric, and one of the components of the metric is the gravitational potential. All those fields are fluctuating quantum mechanically, just like all fields today are fluctuating quantum mechanically. So during inflation, there are these quantum mechanical fluctuations I'm plotting now one mode. And then at some point, the wave number of that mode, come back over here. Inflation happens when that mode is inside the horizon, you have quantum mechanical fluctuations. Then it leaves the horizon. That is, K inverse becomes bigger than that scale. At that point, the mode stops fluctuating. And it turns just to become constant. And at this point, there's also a very profound shift from quantum mechanical to classical. And then it remains constant even after inflation ends because it's still outside the horizon, right? So it's only when it re-enters the horizon at very late times that it begins to evolve. So, for example, the gravitational potential, if it might, during radiation domination, might begin to decay, and then matter dominated during constant, and then decay during dark energy or something like that, right? So that's the way it might evolve. So that is a picture of what a mode looks like. Is there a color chalk here? Well, you don't have a colored pen, so I won't make you do it. So that's for one mode. But if you imagine a different mode has a slightly, say, longer wavelength. So that left the horizon earlier, and that, but same thing. And re-entered the horizon later. So modes that left earlier come back in later, and that began evolving later as well, right? So that's the basic idea. Two different, and then yes, that's the idea. And sorry. This is so there are two phis here. One is the scalar field that drives inflation. This is the gravitational potential that everyone has been talking about until now. Those two fields are coupled. This is a component in the metric. The metric, remember Nalima showed you those bubbles that all talk to one another? So the metric talks to whatever stuff there is. If the stuff happens to be the scalar field, it talks to that scalar field there. So there are equations that relate those two. So let's see, we go till 12. Good, so we're in good shape. So let me, yeah.
So I thought that only both perturbation whichever mode goes out of the horizon, it's generically match or
Yeah, I don't have anything. Maybe Caitlin, do you want to say something? Okay, so you're way advanced from the level I'm at here, so I have nothing interesting to say, but you guys should talk. But just to bridge the gap a little bit between what you guys are talking about and this very cartoon picture, one way to think about these perturbations, this isn't the way that I like to calculate it, but one way to think about them is to think that in one region of space there are going to be perturbations, right, in this scalar field. So that means in one region of space during inflation, the scalar field will have one value, and at another region will have a slightly different value, right? So the difference in those there'll be some small difference in those values, right? And that means that it's only at a later time that the scalar field will catch up to the value at this time. Remember, it's slowly rolling. So one way to think about that is to say that let's see if I have this. Is to write it like this. To write that so what does that mean? That means that in this region of space, the scalar field, this field is dominating the energy density, right? So in this region of space, the energy density is something, and that means nominally the scale factor has some value. In this region of space, the scalar field is something, and the scale factor A has a slightly different value, right? And so we don't allow scale factors to vary with space, right? Because it only depends on time. So the way that we encode that is by putting in these gravitational potentials. So the gravitational potential, roughly speaking, is the difference in the scale factor, the fractional difference in the scale factor between those two places. Because remember that Manoj actually just wrote it on the board. The metric had the spatial part of the metric had an a squared times 1 plus or minus 2 phi, right? So if you think of the scale, if you're thinking of the scale factor in varying two places, really what you're thinking of is the gravitational potential being slightly different, varying from place to place. That's qualitatively. And then once you have this, then you can write this thing in terms of a dot over it. Write this as a dot times delta t over a, and so this becomes roughly h delta t. And then you can take it a step further and then write it as delta t is h times phi over delta phi over phi dot. So that gives you some sense of the amplitude of the perturbations. So even right here, you can almost stop and say that these are the fluctuations. It's going to vary from place to place. The RMS fluctuations then will be of order of the Hubble rate, which is roughly going to be constant. If the energy density is roughly constant, so is the Hubble rate. You have these fluctuations in the scalar field. Phi dot is roughly constant because things are slowly rolling. So what that means is, or should I write it slightly differently? No, let's just leave it like this. So what that means is the RMS in phi is roughly constant, simply because at least for slow roll models where phi dot is changing slowly. So the what do I mean by constant? So this mode over here, which is a smaller wavelength than this mode, it left the horizon later, is going to roughly have the same RMS as this mode. The only difference between them has to do with the value of phi dot and h, the difference in the values in phi dot and h at these two times when the two things left the horizon. But those things are pretty close to one another because both h and phi dot are pretty close to one another. So dynamically, this dynamical mechanism for generating perturbations tells us that the amplitude of the RMS of this wavelength is roughly the same as this wavelength. And what does that tell you? That tells you that k cubed p phi is constant, is scale invariant. I think that's about all I want to say. What? So those are two different K modes. Yeah. So this is a lightning review just to give you a sense of it. Question?
Should I really think of quantum fluctuations as turning off, or like macroscopic correlation? Are they turning off in an average sense, or are they really quantum mechanically turning?
Okay. Okay, good question. I didn't understand the second part of your question, but what I claimed is they stop fluctuating, and they just remain at the amplitude the last amplitude when they left the horizon. And so the language that people use to explain this quantum to classical transition is squeezed states. And the person who's been the most I think there's an article by Andy Albrecht that I'll try to put up in the wiki. I've been putting stuff in the wiki, by the way, that you might want to look at. But it hasn't really been well developed, this whole idea. So, and I certainly I'm not equipped to talk about it. But that's the basic idea. I think that it's a squeezed state. So it's obviously everything's quantum mechanical in nature. But because it's a squeezed state, there's not the same degrees of freedom. So the quantum stuff transforms itself to classical. And so and another way, so that's the hard part. That's the very profound hard part. The very easy part is to point out that this quantum mechanics is taking place on microscopic scales, right? And then physically, the scales are being blown up by inflation by astronomical things until they're literally form galaxies, right? So galaxies, the largest things in the universe, are the end result of these microscopic quantum mechanical fluctuations. Precisely how that transition from quantum classical happens is fascinating, but the simple idea, the almost simple idea, is that you have microscopic to macroscopic, and that's what's really interesting. Yeah. Yeah. Yeah, I guess that's one way to think about it. Right, so it's not a robust prediction. You could get inflationary models that have much closer to scale invariance than what has been measured. So it's not, but a vast majority of models are all over the place. They're close to, but not there. So in that sense, it's nice. It's not. I wouldn't say it's a hard and fast proof of inflation, but it's a pretty nice thing to have happen. That it's not scale invariant, or that it's close to scale invariant? Well, like you said, I think what you said is correct. It ends, so we know phi dot is not zero, right? The thing, if you run in potential, phi is slowly rolling, right? So the value of phi at some later time, when this guy left the horizon as opposed to when this time, is going to be slightly different, and therefore h, which depends on the energy density, which is this thing right here, is going to be slightly different. So we expect it to be slightly different. Yeah. Other questions? Yeah. Yeah, I don't have much to say about that. Interesting. Except to say that there doesn't seem to be much room for them observationally. And qualitatively, what they are is they don't really affect the gravitational potential. Most of them just compensate. So you have the baryons have some overdensity, and they're compensated by some other species and stuff. Okay, that was the third thing. The fourth thing I want to talk about is from the sublime to the practical, galaxy surveys. So this is just an overview. This is kind of like Fermilab, LHC, CMS, Atlas, just in one table. This will take 3 seconds. There's a nice review that gives a one-page summary of the characteristics of about 10 different things going on that I put on the wiki. That's a handy guide. But roughly speaking, let's talk about each survey, a bunch of surveys. Let's talk about how much area they cover. Let's talk about what type they are. I'll explain that in a second. Let's talk about the galaxy density. How many galaxies they measure. If you have if you look out with your eyes, you're going to only see one galaxy per the whole sky, Andromeda, right? Because that's the only one you can see with your naked eye. So if you have a slightly more powerful telescope, you can see more than one galaxy per the whole sky. And if you have a very powerful telescope, so the more powerful your telescope, the more galaxies you see. And the limit is us. So we're the lower limit, right? So anyway, that the galaxy density, clearly the more powerful your telescope, the more galaxies you're seeing. And I think that's about all that's about all the information I want to give you about each of these things. So the one that I'm working on now is called the Dark Energy Survey. That will ultimately cover 5,000, and these units are square degrees. That will cover 5,000 square degrees. Remember, there are 40,000 square degrees on the sky, so this is about a factor of about 1/10 of the full sky. This is what's called a photometric surveying. And what that means is we measure the positions of galaxies very accurately. We know exactly where they are on the sky, but we don't know how far away they are from us. The way to do that would be to get the spectrum of the galaxy. That tells you how rapidly it's receding from us, and that, using the distance redshift relationship, tells you how far away it is. So if you knew its spectrum, you can get its redshift, and you can make a 3D map of the universe. These things are photometric, which means they're really 2D maps of the universe. Does that make sense? The only qualification is that we take images of the galaxies in 5 different bands, optical bands, and so a spectrum of a galaxy is a function of, say, wavelength. Is complicated. It's got peaks and troughs and stuff. And people who study galaxies know exactly, they would know exactly what kind of galaxy this is, and they'd say, oh, that's the O2 doublet, and that's shifted by whatever, and that tells you the galaxy is at redshift 0.7 right away, right? There's people who do that for a living. So if you had a spectrum, you'd be able to tell exactly how far this galaxy was. A photometric survey only measures it in several bands, like in 3 or 4 bands. So it gets all the light in here, all the light in here, all the light in here, all the light in here. And so you can create a crude estimate of the redshift just based on these bands, right? And so those are photometric redshifts. They're actually not that inaccurate. This is maybe the most important thing people are working on in DES right now. It's interesting. And one of the fascinating things that I like to say is, so look at me now. You only see a 2D projection of me on your eyes, but you know that my nose is close to my mouth, right? And so you're using you know that my mouth is not over there and my nose over here. How do you know that? Nah, it's not enough, I don't think. I don't think that does it. That does it. Close your eye. Close your one eye. You still know it. You hear it? You can't hear my nose, I hope. But the reason, okay, maybe your 2 eyes help you, but again, if you're blind in one eye, you would still know, I think, that my nose was close to my mouth. And part of it is you're using the color information. You see that the color of my face is different than the color of the blackboard, so you know that my face is all one thing, and that's behind me. And you're also using clustering information. You know that noses are often close to mouths. So you know my mouth is not over there and my nose over here, right? So you're using color information and clustering information. And that's what we're trying to do. Historically, people have used just the color information to get photometric redshifts, and now we're starting to use clustering information also. So it's actually a fascinating field. It's really interesting. How to transform a photometric 2D survey to a 3D survey. The galaxy density in the dark energy survey, we tend to the best way to do it is per square arc minute. The more galaxies, the better. DES will have about 10 galaxies per square arc minute. The next version of this will come online in so this goes from 2013 to 2018. LSST will start in 2022 roughly to 2032 roughly. That will have 20,000 square degrees. It will be the same kind of survey, and it will go much deeper. So it'll be much bigger and much deeper. And then the last one, again, there's the review article that David Weinberg spearheaded that I listed in the wiki is quite nice. It's called the Dark Energy Spectroscopic Instrument, and that one will cover 14,000 square degrees. It will be a spectroscopic survey, so it will have spectra for lots of objects. But it's very expensive to take spectra, as you would imagine, because you have to get light at all wavelengths. So there's many fewer galaxies per square arc minute. So that's an overview of these things. So this is the way we're going to. These are the surveys we're going to use to try to get at this matter power signature, to get at the physics of dark energy, get at the physics of neutrinos, get at the physics of inflation. Questions about that? just the light you get, and there's some units there, like light per square centimeter per second.
Actually, the light from the galaxy, like stars.
Yeah. So it's all, most of the light from galaxies is I don't even know. But anyway, there's stars in galaxies. There's gas. There's lots of stuff. The instruments. DES is a 570 million pixel CCD camera on the 4-meter telescope, the Blanco telescope in Cerro Tololo in Chile. LSST will be right nearby in Chile. That will be an 8-meter telescope. DESI is also going to be on a 4-meter telescope in Arizona, and that will take spectra. Okay. So that's the fourth thing I wanted to say. The fifth thing is I want to walk through one example that is, so we have 20 minutes, so this is good, is a beautiful calculation. I think everyone should know this calculation. And it comes up again and again and again in cosmology. And so so we should do it. And so let's do it, assuming that you're interested in analyzing data from a photometric survey, DES. So what I'm interested in is galaxy clustering. In a photometric survey. So a photometric survey means that we can form delta of galaxies. We can form pixels on the sky, right? And each pixel we can measure the number of galaxies, and we subtract off the average number and divide by the average number, and that gives us delta, right? So that's an operational way to do it. So we can form it, and that depends on the position on the sky, right? But because it's a photometric survey, in principle, we don't know where any of those galaxies are, right? So what this is really a measure of is an integral over distances out from us all the way out to infinity of the number density of galaxies per distance times delta, the 3D distribution of galaxies. Let me get rid of the subscript here. At a 3D position x that depends upon the distance and the angle theta. Okay, so first of all, let me just say what that 3D distance is. We're going to make a simple approximation where things are clustered around the z-axis, just to make things simple, geometry simple. And that turned out to be a pretty good approximation, even for something like DES. So then the perpendicular coordinates are just equal to d theta, right? So here's the geometry. We're sitting over here. This is the z-axis. This is the angle theta. So this is the perpendicular co-moving distance. That's equal to d times theta, right? Just this is d and this is theta. So just the small angle limit's d theta. And then the radial distance is just d. There's a small correction, but that's of order theta squared, and we're assuming theta is small. So that's the 3D distance. This is almost right. The one thing that's slightly different is we've reserved this for the matter overdensity, and that's what we're interested in, right? Because we have predictions for the power spectrum in terms of physical stuff, in terms of physics. So that's great, but that's not exactly true because that assumes that galaxies form. The galaxy overdensity precisely traces the matter overdensity, and that may or may not be true. So there's some fudge factor here, and if one thing that people do is they just put in a number here that they call the bias, which is the relationship between the galaxy overdensity and the matter overdensity. And again, this is a whole area of research that exactly what to do. But for our purposes, I think it's we can just say that the bias on large scales is roughly constant. So this is just a nuisance parameter, but it's not. It turns out to be not that. Let's just forget about it. It's annoying and it's there. Okay. So anyway, so this is the thing, right? Okay. So what we'd like to do is look at the statistics of this, because you can see the statistics of this thing are related to the statistics of what we want, right? So the goal of this calculation is to relate the 2-point function of this to the 2-point function we know. Got it? All right, so let's do that. First of all, let's take the Fourier transform, because we know that the thing we're interested in is the Fourier transform of that thing, because that's the power spectrum. So if we Fourier transform this thing, we take delta G twiddle of L, and in our conventions, that's equal to the integral d2 theta e to the minus I L dot theta times this thing, there's a bias, and that's the integral over distances, dn dd. And then there's that 3-dimensional matter density. Let's Fourier transform that too. So that's the integral d3k over 2 pi cubed. Then it's the Fourier transform of the matter density. And then it's got this exponential, which is e to the I. The perpendicular part of the wave vector is dotted into the perpendicular part of x, which is just equal to d theta. And the transverse part, the radial part, kz, just multiplies d. Do you agree? So that's that. And then we have a very simple thing that happens here. The theta integral just gives us a delta function. L is equal to k perk times d, dotted into times d, right? That gives us a delta function. So we can do the perpendicular component of the part of the 2k perk integral on this thing using that delta function with one little twist. What's the twist? You got to divide by d squared, right? Because it's a 2-dimensional d squared delta function, right? Does everyone know that? All right. Yes. All right. So then this goes away. 2 of these go away. Let's count the number of integrals we've done. 1, 2, 3, 6. So we've done 6 integrals. We start out with 6 integrals. We now have dd, dn, dd. And then we did the d2, and then there's 1 over d squared, because that came from transforming the Dirac delta function in terms of k perk to do the k perk integral. And then we have just a remaining integral over dkz over 2 pi times e to the I kz d. And so that means, if I did that right, there's delta twiddle of k of now k perk is equal to L over d, and there's still a kz. Do you agree? So that is the thing. We're left with 2 integrals, which means we started off with 4. So with 6, and we've done 2. So just to be macho about this, let's write down the number of integrals we've done so far. We've done 4 integrals so far. All right, so we're interested in the 2-point function of this, right? So the 2-point function of this, delta G twiddle of L times delta G twiddle star of L prime, we know that the expectation value of that is equal to 2 pi squared delta 2 of L minus L prime times CL. Right, these are not the CLs of the CMB, these are the CLs of galaxy clustering. But it's the same 2-point function, the same statistics, right? So in order to get the CLs, which is what we want, that's the stuff you put on money plots of the CLs, right? So we want to get this. In order to do that, let's integrate both sides over L prime. Then you get rid of this delta function, and you have an expression that CL is just equal to the integral d2 L prime over 2 pi squared times the expectation value of that 2-point function. So just this thing squared. So that's the integral dd over d squared dn dd times the integral dkz over 2 pi e to the I kz d. That's one of them. And then another one, the integral d prime over d prime squared dn d prime has the integral dkz prime over 2 pi e to the I kz prime d prime. And then we have the ensemble average of the delta twiddle of L over d kz with delta twiddles, oh, there's a minus sign here because we're taking the complex conjugate. Delta twiddle star of L prime over d prime kz prime. Do you agree? Okay, so now we're left with 1, 2, 3, 4, 6 integrals. All right, so the let's see, how should we do this? How should we do this? The this thing here is a delta function, right? This is the 3D density, and we know this is just equal to a delta function times the power spectrum, right? Are you guys with me? We're all in on this? Okay. This is a beautiful calculation, just to motivate you. All right. So if it was really beautiful, I wouldn't have to tell you that. So this thing is we know what this is. This is I wrote this down last time. We know what this is. This is 2 pi cubed times the Dirac delta function in these things. So let's break it up into a 2-dimensional Dirac delta function which sets L over D equal to L prime over D prime. That's one of them. And then there's a 1-dimensional Dirac delta function that sets Kz equal to Kz prime. Right? That's what that is. And you multiply that by the power spectrum. And the power spectrum is the square root of L over D squared plus Kz squared. Right? So that's what that is. Okay. So now the L prime integral, L prime appears only one place, and that is over here. So we can trivially do that integral as long as we multiply by a d prime squared. So that gets rid of this integral. And then the kz prime integral just sets kz prime equal to kz. So we'll just get an e to the I kz d minus d prime. So what we're left with is the integral dd over d squared dn dd. And then there's an integral over dd prime. The d prime squared goes away because when you take the derivative, that d prime squared kills it. So then it's just dn dd prime. The kz integral is still here. So that's the integral dkz over 2 pi. And then we have this exponential e to the I kz times d minus d prime. And then the 2 pi's, by the way, all work themselves out. And that's the nice thing about this convention. And the only thing left is the power spectrum, which depends on the square root of L over D squared plus KZ squared. Okay, and meanwhile, we've gone from 2, 3, 4, 5, 6 to 1, 2, 3. So I give myself another 3. All right, so this is the intro. Until now, we've just been doing math. Now we're about to introduce beautiful physics. Any questions about this up to this point? Okay, here's the beautiful physics. Look at that inner integral. The inner integral has this oscillating function over kz times some combination of distances. And it's multiplying a power spectrum that depends on L over D and KZ. So think about the following two scenarios. We're sitting down here, and we're looking at what we're doing this is we're summing over all possible Fourier modes that contribute, right? So let's think about these Fourier modes. Which ones are contributing? Well, look at a mode like this, which varies like this. So this mode has kz times d kind of much bigger than 1. That is, things are varying a lot in this direction, right? So kz is pretty big. So for that mode, this thing is going to be huge. So you'll have oscillations up and down, up and down, up and down. So even when kz changes by a little bit, this thing is roughly constant, and you're just going to get cancellations. So that mode is basically not going to contribute at all. And physically it makes sense. Why? The modes that are like this physically, they're not going to contribute, right? Because we'll just look along this line of sight and we'll see zero. We'll see cancellations, right? The modes that really are interesting in a two-dimensional case are modes that look like this. Right? These are modes in which kzd are less than or of order 1. Right? So for those modes, when we look along the line of sight, we're seeing a full, say, overdense region or a full underdense region. And so we're getting coherent sum over all time. So it's the low kz modes that are really contributing to these to the overdensity we see on the sky. That's the physics. How does that manifest? How does that translate into the math? It's the low kz mode. Let's say L is large. L is 100, which corresponds to a degree scale or something like that. So if L is 100 and kz is of order d, those modes over there, then L over d is way, way bigger than kz. So you just take out the kz itself. For the large kz modes, those are just going to be 0. So the only time you get a non-zero contribution are the modes that have kz that L over d over here dominates over kz. And that means you can take this out of the integral. Because all that depends on is L over d. The large kz stuff will just go to 0, and the small kz stuff, you're just left with L over d. So what we're left with is this beautiful formula that CL is equal to the integral over all distances over d squared dn dd. Now, when I take this out front, this is just delta function in d minus d prime. So I can do that integral. So this just becomes dn dd over d squared dn dd squared multiplied by the power spectrum evaluated at k equal to L over d. And that's it. And I'll give myself 2 more chalkboards. Okay. So we did 9 integrals in 15 minutes, and we got this beautiful formula. It's beautiful because, and this is called the Limber Approximation. It's beautiful for 3 reasons. First of all, we use it. Second of all, it tells you physically what's going on, which modes there are that contribute, right? It's the modes that have those large kz. And there's a bias squared here, I guess. And there's another reason it's beautiful, but I forgot it. Anyway, okay, so that's the answer. Any questions about that? Then in that point, this term is just huge. Because remember, L is 100. So then kzd is going to be 100. So this is just huge. It's just oscillating up and down, up and down. Up and down. Yeah. So this, I won't say it. Yeah.
I understand the math, what's going on, which part is 0, which part is but when you make that kind of visualization of the mode,
Yeah.
is it really the correct picture or visualize something?
Yeah, this is a very nice intuitive way to think about it. In fact, I'll come back to this question in a second because I just remember the third reason it's beautiful. The third reason it's beautiful is that I did this with the density, but it turns out in cosmology, the name of the game today is cross-correlating different probes. And so we can, for example, cross-correlate the galaxy overdensity in DES with the CMB lensing field that we'll talk about next time. And those things require you to do the exact same Limber Approximation thing. So this is a ubiquitous formula. Everyone's always using it all the time. So you have to know this formula. Okay, getting back to your question, another way to think about this is another beautiful way to think about it, is the clustering. You can rewrite this as with a new dummy variable, call it k, to be L over D, right? And then what you get is this thing is roughly, don't quote me on this, is roughly k cubed pk. That's what you'd expect. That's the fluctuations, the RMS fluctuations. But it's suppressed by some factor of 1 over L. I forget what the factor is. And why is that? It's because not all k modes are contributing. Only the k modes with small kz are contributing. So think in Fourier space. Right? So there's a sphere in Fourier space for a given k. Right? But the only modes that are contributing are those modes with k's equal to 0. So they're in a small annulus around it's centered around in the kz equals 0 plane. So that means count up the number of modes in a shell of width dk. That's 4 pi k squared dk, right? And then it's not all those modes are contributing. It's only a fraction of those. Which fraction? The fraction in the annulus, where the annulus is 2 pi k dk. So what you're left with, the fraction of modes that are contributing is given by that ratio. So that's another beautiful way of thinking about it. That the fraction of modes are contributing are that, and that if you rewrite this in terms of integral over k, you'll see that suppression between the naive RMS fluctuations. It's suppressed by precisely that fraction, the fraction of modes that are contributing. Other questions? That's 4, right? Yeah, it's a good formula. Okay, so we have 30 seconds left, which gives me a chance to say the following. The matter power spectrum is key. That's what we're after. That's how we can learn about dark energy, dark matter, and neutrinos and inflation and stuff. This is one way, galaxy clustering. Another way is to look at galaxy clusters, very big objects. Manoj touched on them. They're very rare things, so they're sensitive to the RMS, the fluctuations, which in turn is sensitive to the power spectrum. Another way is supernova, which you've heard of, and then another way is to talk about weak lensing, which is what we'll do totally tomorrow. But the one thing to think about in all these different probes of getting at the power spectrum is some of them, like supernova, measure distances, right? And that's how they're sensitive to dark energy. They measure distances as a function of redshift. And similarly, you can see here, the clustering gives you some information about redshift, about distances in there. And similarly, clusters and weak lensing have information about distances. But these, clustering and weak lensing, give you information about the growth of inhomogeneities as well. So instead of thinking about W, which is the equation state of dark energy, what I think we're beginning to move towards is thinking about measuring cosmic distances very accurately with supernova, with some of the kind of features in some of these probes, and then measuring the growth of structure. Those are two separate ways of doing things. And by doing that, we're kind of at the percent level here, and we're at the 10% level here. By doing that, that's how we're going to make progress figuring out why the universe is accelerating today. That's it. Let me just see if I got anything on this thing. 1 second, sir.